This radiation, which is radiated from the sun surface or solar surface, or from the photosphere, which is also called as photosphere, this reaches the Earth. This reaches the Earth surface, and this radiation is of two types. One is direct radiation, that's called as beam radiation. A beam coming directly from the solar surface or photosphere and reaching the Earth atmosphere, which is called as beam radiation. And diffuse radiation. Diffuse radiation is because you have gases present, you have dust present in the Earth atmosphere, and then on the Earth surface, we get this radiation from the sun, which is in diffused form. So solar geometry is very important with respect to the Earth. That is the position of the sun in the sky and the direction of this beam radiation on the surface with various orientations. So that we will also look at. So as we said, this sun is nothing but this a body which is radiating energy, and then this is also known as effective black body, where the emissivity is nearly equal to 1, and with the surface temperature of 5000 Kelvin. So this is a very important factor in order to do any simulations or experiments, in laboratory experiments. For example, if you plan to look at say performance of solar photovoltaic systems, the photovoltaic material that you produce in the laboratory, this photovoltaic material or photovoltaic panels, you can simulate the sun, and you can test these panels by what is known as sun simulator. So sun simulator is a perfect sun simulator. It should radiate what is sun is radiating in this wavelength of 0.25 to 3 microns, and it should be having an effective surface temperature of 5000 Kelvin. So there are sun simulators or solar simulators available, which people use for research purposes. So we are just to understand, what is happening. We are having this recap of solar energy, just to keep perspective for the discussion. So you have these fusion reactions where hydrogen combines to form helium, and there is a loss in mass, and this reaction is converted into energy. So 90% of energy is generated in the core of the sun, as we discussed, and the temperature is of order of 10⁶ Kelvin. 10⁶ Kelvin. Now this energy is transferred out to the sun surface and then radiated into the space. So to understand how much of this radiation coming out of the sun onto the Earth's surface, we have to understand the geometries. So fortunately, we are not very close to the sun. There is a lot of distance that the light has to travel. So this is 1.495 to 10⁻11 meters. That is the distance between sun center to the Earth center. And the diameter is also, for the Earth, the diameter is also smaller than the sun. So if you look at now, because of this large distance, what happens is that if you take a surface on the Earth surface, or take a point on the surface of the Earth, so this is a point, and this point, so you look at the diameter, look at the sun here. So sun will sustain this angle, which is of 32 minutes. So this energy is getting radiated on the Earth's surface. So sun radiations are coming onto the Earth's surface with this angle, that is 32 minutes. Okay, so this is what is depicted in the figure. So we know that this distance, whatever we have written, that is 1.495 to 10⁻11 meters. This distance is variable because we have the Earth's orbit, which is not perfectly circular. It is eccentric, Earth's orbit, and that's why you have this variation. Further, the Earth is also not like this. Earth rotation and sun with respect to sun. So if you look at the axis of the Earth rotation, this axis is inclined, and that's why we get what is known as declination. So on the Earth's outer atmosphere, so this angle is on the Earth's outer atmosphere, the sun subtends an angle of 32 minutes, and because of this very, very small angle, you see that the radiation that is reaching the Earth is almost constant, so fairly constant. The intensity of the solar radiation is fixed intensity, nearly fixed intensity. Okay. So this intensity, what is that intensity? So you can measure now because there are techniques where we can go. Now there are space stations built outside the Earth atmosphere. So outside that Earth atmosphere, we can certainly now measure, and these measurements will vary a little bit, but we can find out what is the radiation reaching the extraterrestrial atmosphere or extraterrestrial, that means outer atmosphere. So outside the atmosphere we receive 1353, that is 1353 watts of energy, joules energy per, that is power basically, energy per unit time per meter square. Okay, so joules per second per meter square. This much of energy with the variation of 1.5% of energy is reaching the outside atmosphere. So this is directly the beam radiation. Now this is important for our satellites, for example. So when we launch a satellite, we know that on the satellite there are lots of onboard power requirement, and this onboard power requirement is satisfied by using what is known as solar panels. And these solar panels should operate, should be able to absorb this much of radiation, should be stable, so that they would be should be stable so that they can so that this energy which is received outside the atmosphere is a fixed amount of energy with little variation. So you can design basically your solar panels. So solar thermal energy conversion is very less utilized, but we sometimes also require to modulate the temperature of the electronics. So say for example, if there is a camera on the satellite, that camera should operate, or some instrument, some measuring device that should operate at some certain operating temperature. So that is an optimal operating temperature. So in order to maintain that operating temperature, we may go for solar thermal kind of, like where we are not actually looking at the fluid, because the fluid is zero gravity basically, but there could be a phase change material and it would maintain the temperature. So but more or the less, it is more of solar photovoltaic energy collection is what happens in extraterrestrial atmosphere on the space stations. So this is the energy that is being received, and this energy is diminishing. We should keep this in mind, that this energy watts per meter square is probably measured some few years ago, but we have constantly monitor this solar constant, which is denoted as GSC. Solar constant, or SC is for solar constant, and this is diminishing because the core itself is diminishing for the sun, and but it will take millions of years from now. So there is a World Radiation Center, on the other hand, has adopted a value of this 1367. So some books you might find that this is written as 1367 watts per meter square, and there is again uncertainty that they have adopted, which is again 1%. So which is, this is the total energy that is available in the solar spectrum. So what is being total energy available in the solar radiation is this, but this is distributed. This is distributed in various spectrums. So it is important to understand that there are various activities happens on the sun surface, and such as, for example, solar flares or solar storm. So what happens is that these activities on the sun surface will will vary these the solar constants, or will affect. For example, they might affect the solar panels, and it might affect the atmosphere on the Earth's surface. But for solar thermal energy collection, we are not so much bothered about these activities, solar flares. We see that for solar thermal energy collection or solar collection on the Earth's surface, we are more worried about the weather conditions. Okay? So because of these solar flares or solar storm, we know that we need to protect the electronics, that is onboard electronics on the spacecraft from these solar flares. So solar physics is now, because of these all things, it is a branch of various disciplines. So that's why we say that it intersects many disciplines such as physics, for example, the fluid dynamics, astrophysics. Physics is astrophysics, and the plasma physics, space physics, spectroscopy, radiative transfer, heat transfer. Okay, now also electronics is also involved. So that's why it is of important thing. So what we should now understand, that this energy that is reaching the outer atmosphere is having a distribution, which is known as spectral distribution, because the energy is not radiated in a particular, is not concentrated in a particular wavelength, but there is a wavelength range. So if you look at this wavelength, with respect to wavelength, what is the irradiance? Irradiance is defined as the power received per unit area. So power that is received in the per unit area in a particular wavelength range, okay, as reported from the measuring instrument. So this we can measure outside the Earth atmosphere or on the Earth's surface, and we can distribute the energy in the various wavelengths. So this is how it is distributed. Most of the energy is distributed in the visible length. So if you look at the ultraviolet range of the wavelength is basically less than 0.38 or 0.3 or 0.4 microns, and visible range is 0.4 microns to 0.8 microns, and infrared is more than 0.8. So portions of the spectrum is with this, it is 0.064% or basically 6.6%, and this is 48%, and this is 45%. So the energy that is received on the Earth's surface, that is distributed among these wavelengths like this. So say for example, ultraviolet energy is 87 watts per meter square, and visible and infrared is in 656, and infrared is in 623. So your photovoltaic devices, for example, they can probably work in particular wavelength range depending on the material, depending on the cost of the material. You can try to trap different amounts of energy in a different spectra. So it is possible. So this energy that is average energy. This is averaged over the year. So because there are these extraterrestrial radiations, they vary. This vary because what is happening at the source. So variation from the source, that is sun. This variation again we have looked at is could be because of the sun flares, or could be because of the sunspot. Sunspot is basically where you don't have any convective cells on the sun surface, and and we also know that the solar constant is decreasing slowly. That is what I had mentioned. It is decreasing at rate of 0.02% per year, and there is a variation due to Earth and Sun. This should be sun distance. That is plus minus 3.3%. So this variation is because you have variation in the distance because of the eccentricity of the orbit, and depending on the nth day of the year and also nth time and the location, we have this variation. So this solar radiation basically we have to assess. Now for India, we have this Ministry of New and Renewable Energy, which we call as MNRE. So the government of India had launched National Solar Mission. So in the National Solar Mission, which is launched in 2010, where they started to have or started to build a network of solar radiation resource assessment. So these assessment stations, they will understand what is the solar radiation along with other different parameters. So they have been built to have the high quality ground measurements, so on the surface, basically on the surface measurement of the solar radiation data in the country, so that we can design, so that we can have a reliable data. Until 2011, that means only 8 to 9 years ago, we didn't have any much reliable data. So it was very unreliable earlier to that. So that's why the government started building these stations, just like weather stations. So a major hurdle in the implementation of the solar project. So that was a major hurdle because lack of the data. So now we have the reliable data, and over the years we are collecting that data. So there is a lot of data available, okay, at that time, and data that was available earlier was only with Indian Meteorological Department (IMD), but now you can get that data from MNRE or from what is known as National Institute of Wind Energy. So NIWE is responsible for operation and maintenance of these SRRE stations, and we can get that data. This data would be available. This data would be available for our this data would be available for the understanding of the solar power. So it could be solar thermal, or it could be to build a solar, say, photovoltaic, or even solar floating solar photovoltaics, or any other technology. So where we can use that data, so available resource data. So now we can map basically. So this SRRA is to collect the solar radiation resource data and associated meteorological parameters. So it also, along with solar radiation, it also collects some meteorological parameters. And this is the established world's largest solar radiation monitoring network. So we should understand this, that we have invested a lot. And if you look at the, I am not covering the energy, mix basically. Energy mix or energy security of the country. If you look at worldwide also, we are going ahead with solar photovoltaics and renewable energy resources. We know that we are going to have, India is going to have by 2030, lots of projects. There are many projects happening. If you look at the government infrastructure website, you will see there are very much large stations are the projects are under construction, majority in the southern part of India, and most of our Rajasthan desert area and all, we are still building large power stations. So by 2030 or so, we will have a large contribution from solar energy. Until now, we know that we rely more on the coal and fossil fuels, and to have the energy security for the country, I think we should decrease our consumption for the fossil fuel, that we all understand. So that this will also boost what is known as the solar or electric vehicle projects in India. So this is very important, that we have the data available, and then we can now process that data. Okay, so data processing is very this is a challenging task. How do you find out, how do you optimize, how do you do site selection by using this data? So data is available. We need data engineers for this. Okay, so and then these data engineers should talk with the mechanical engineers and civil engineers and physics people, so that they come up with a solution which is very much tailor-made for that particular location. So we have this network of SRRAs, and you can search the website. And these SRRA stations generally consist of 2 towers of 1.5 meters to 6 meters tall. I have taken it from their website, that NIWE website. Similarly, you have NISE, that is in National Institute of Solar Energy. So this is a map where you could see that in this map you could see the station all over the country. All over the country you have the stations where you are collecting the data. And this data is collected by solar radiation measurement. And you can measure this by using these two measurement techniques, that is pyranometer and pyranometer. Basically, pyranometers will give you watts per meter square, direct and diffuse radiations respectively. Okay, so 6 meter tall, another tower is used for meteorological sensors also. So now, because we have made a lot of progress in sensing technology or sensors, so we can sense, we can have the indigenous sensors developed, and this is a meteorological sensing. That means weather sensing, and for that temperature, Anyway, is the one of the parameter: relative humidity, atmospheric pressure, wind speed, and direction. So wind is another data that we require. Rainfall and state of art data acquisition system. So there is a data acquisition system and lot of data is available, which is sampling at 1 second, and basic data average is 1 minute. So that means we are collecting the data, and we also know that this is corresponding to the energy that is reached on the Earth's surface. So to understand the energy reached on the Earth's surface, and to understand the particular location and its relation with the sun, there are angles. So I'm not going in deep about these angles. I'm just putting this slide as an informative slide, because these angles one should understand in order to track the sun, because sun is not glowing or not shining at a particular location in the sky. Sun is always moving, or you can say that is because Earth is moving. So if I stand on Earth, with respect to me, the sun is moving continuously, and it is changing, as you know, in the day and also in the year. So in order to understand this, how it is changing, we need to understand the location. So if the P is a location, then you can find its latitude and then various angles, say declination and all. So delta is declination. So beam radiation is the radiation that is coming from the center of the sun. So this is your beam radiation, and received from sun without having been scattered. And diffuse radiation is when it is scattered. So this figure shows this various angles, zenith angles and all. So this is direction, where zenith direction is basically normal direction to the surface. And these angles are very important. So why these angles are important? Then you can track. So if you know how the sun is moving on a particular day of the year, then sun's location basically, or with respect to this surface, then you can track the sun and you can move this surface, so that always you are getting the beam radiation. Beam radiation is where it is it is not diffuse, so you probably have the full spectrum of energy. But diffuse radiation, you may not have that much of energy available in the diffuse radiation. That is, suppose that is very evident. If you have a cloudy weather, then you do not have that much of energy available. So if it is clear sky, sun is shining and your surface can see the sun, and then there is a beam, and then you can harness that spectrum. That is all the energy that you have. So how to get this energy? So this energy you can harness by using various techniques, and solar thermal collector systems are one of the techniques. So it is basically solar thermal. Generally, if you talk about solar thermal power plants, okay, the power plants is generally used. The term power plant is generally used when you change or when you convert something into electricity. So there are solar thermal power plants where the power plant is working on the thermal cycle. Basically, that's why it's called as thermal power plant. And there is a Rankine cycle that some of you know that most of the thermal power plants work upon. So this solar thermal power plants will also work on that Rankine cycle, and you can probably harness this solar energy by using photovoltaic conversion, that is directly convert the sunlight into electricity, or by using solar thermal conversion. So photovoltaic conversion or solar thermal conversion, where you convert the solar radiation into heat into using some working fluid. So there are, apart from this, so these are called a direct conversion. So directly you can convert your solar energy in this form or that form. So there are other methods basically which are called as indirect processes, and all what is happening on the Earth's surface, you will be there with me, that is because of the energy that we receive from the sun. And for example, you have this wind. So you know that wind energy, you can derive power from the wind energy, which we call as wind power. And this wind power is again it's derived from the solar energy source. So this wind, you know that it flows because you have you have differential heating on the Earth's surface, and that's why you get a different wind speeds. So similar to that wind, you have biomass. For example, biomass is basically growing in the plants, which will give you the fuel, and you can convert that into liquid fuel, that's biofuel. Say for example ethanol, by using gasifiers. So this photosynthesis of that is making the plantation, and then growing the plant, and then deriving the fuel from the plants. So this is again is indirect process where solar energy is the resource. Energy is the resource. So biomass, for example, again the hydro energy. Hydro energy, you have the differential heating and the evaporation of the water, and then you get a rain. Why we have an evaporation is because of the solar surface, and then that's why we get a rain, and then we stop rivers, and we get this hydro power plants. So the fossil fuels. So fossil fuels are also, you can say, derived because because of the decay that they have over the years under the crust. But the process is indirectly, because of the wind, because of the solar energy, because of the solar energy. So this is indirect processes. So we are not going to look at the indirect processes. We are not going to look at the photovoltaic conversion now. We are only concentrating on thermal conversion. So thermal conversion, yes, you can convert by using various systems, and the very simplest system is this rubber, which we call as EPDM rubber. So this is unglazed, basically this is like a mat. So where you have these flow passages, and this is painted black, and then you can probably put this on the sunshine, and then get some useful delta T, that is rise in the temperature for the fluid that is flowing through these manifolds. There are flat bed collectors where we can use these tubes, which could be an evacuated tube, so evacuated flat bed collectors, and there are parabolic truck collectors, which we see this in little bit in detail. Okay, so solar thermal energy, when we call solar thermal energy, it could be power and electricity generation systems. It will collect, so to generate the power, it will collect and concentrate sunlight or radiation to produce high temperature. So we have to go for very high temperature, so that this high temperature you can create a steam. So heat is required to generate an electricity, and this, for example, conventional coal-fired thermal power plants, or if it is oil-fired thermal power plants, we have conventional boiler. And this boiler, actually what it does is converts the working fluid, which is water, which is easily available, although it is corrosive. But at a low cost is available. You can purify the water and then use in the thermal power plant. And if it is solar thermal power plant, we are still using the water and this water is changing the phase because of the heat, and now this heat is being absorbed from the sun or collected from the sun radiation. So solar thermal systems have solar energy collectors with two main components. That means we need to have reflectors or mirrors that capture or focus the sunlight, and a receiver or absorber which will absorb this radiation. And whenever a receiver where it is getting absorbed, you need to transfer the fluid, because you need to take out from that location. So actual utilization is not where you are concentrating the solar radiation. In the case of power generation, suppose in solar cooker is where you concentrate, and then the actual consumption is there at the concentration location, because you want to cook food, for example. Or solar dryer is where you concentrate the solar radiation. These are all thermal, where you are concentrating the solar radiation, and there you are utilizing it. But for power generation, you need to transfer what is being concentrated, the energy you need to transfer from that location to your other location where you are going to produce by using, say, for example, turbine. So that's why you have to transfer this fluid, and then it could be a low cost working fluid. So the steam is converted into mechanical energy. So water is used, and water is made as a steam, and steam is, that you can pass over the turbine, say for example, following the Rankine cycle, and turbine then generates power to produce electricity. So solar thermal energy collectors are generally non-concentrating. So that means this receiver area or the absorber area is receiver area where the energy is getting received is equal to the absorber area where it is absorbed. So where you are not doing concentration of solar radiation. So the concentration ratio is represented as CR, which is equal to 1. And they are concentrating solar thermal collectors where concentration ratio is greater than 1. So for our generation, where you require very high temperatures, you require a concentrating type, these concentrating type solar collectors. So a flat plate collector is the simplest, what you call simplest flat plate collector, is where the absorber, this is the absorber plate of the flat plate collector. An absorber plate is where it sees the solar radiation and absorbs the solar radiation. And this absorber plate area is equal to the area of the surface area, which is perpendicular to the screen here. So this area is equal to the the receiver area, the energy that is being received. So energy received area is equal to the absorber area. So that is why here you could see that the concentration ratio is 1, and then this is constructed such that you absorb the solar radiation on the absorber plate, and the fluid is passed through these pipes, where the fluid is passed through the pipes, and these pipes are attached. So generally the absorber plate is made up of copper or aluminum, and copper is a very good conductor, so that's why most of the times we prefer copper for the absorber plate, and that's for the tube, and it has to be a black chromium plate. So this unit is the simplest absorption, but we need to add that with the absorber plate and absorber tube. We need to add with the enclosure. The enclosure is required to arrest the what you call as losses, heat losses from the unit. So this enclosure, it could be of say fiberglass or with organic binder or aluminum, or so it depends on how much sturdiness you require. And you require to have cover plates. So these are the cover, inner cover and outer cover plates, and these are the glass covers basically of certain thickness. So if you look at the absorber tubes, we are having these evacuated glass tubes also nowadays, and then in India, Indian that is manufactured in India has started by Borosil, and it is started since 2010. Earlier we used to import, and also now it is not that expensive. The glass tube that you get for which is evacuated glass tube is not very expensive. You can search web to find out more about this, Borosil. So this is a simple. I didn't want it to keep it a little complex about the heat transfer and how do you analyze this. But if you look at that is the Q, which is basically collected energy from the flat plate collector. It can be defined, or it can be related with area of the collector multiplied by the radiation. So this is the radiation that you get, the solar radiation. So solar radiation falling on the tilt, we have to have a tilt because of our location here. It depends on where are you located and the location with latitude, with respect to latitude. And this radiation that is in watts per meter square, you have to multiply by basically the area of the collector. But what we have is this radiation is not directly falling on the absorber, but it is basically you have these glass surfaces. So there is an effective transmittance and absorptance product that is related to your glass covers, and then you can find out this, and this is what is being radiated minus what is being overall heat loss coefficient. So there is a heat loss coefficient from the unit, so you have to estimate UL, and then based upon the absorber plate temperature and the mean fluid and atmospheric temperature, basically this is the loss. So what is being useful, QU, is useful heat, basically gain or useful gain basically, A useful gain is related to what is being inputted, what is being lost. So this is lost to the atmosphere, because atmospheric temperature is something like, say for example, 30 degrees centigrade, or say 300 Kelvin, and the plate temperature could be a bit higher, because you are going to heat, you are going to absorb the solar radiation. So there will be naturally the heat loss. So as you arrest the heat loss, that means this minus part of this equation, or this equation, or this equation. These are the same equations. That depends upon which temperature you are measuring. If you are measuring the mean fluid temperature, then it is F dash is used. F dash is basically the flat plate collector efficiency, and if you are using the plate I PI, then you can this should be TFI. Then it is fluid inlet temperature, TFI, not TPI. It is TFI. It is a fluid inlet temperature. So based upon that, then you can get the FR, which is known as collector heat removal factor. So you can get the estimate of the useful energy gain, that is QU, from this equation if you know certain parameters. So this is more on the performance, and there are various books available. I can introduce the books for the performance. I am not going in detail for the performance of solar thermal energy collectors, but for say flat plate and for parabolic trough, is well written in the books. You can refer to that. So this solar energy collection, so which is a flat plate collector, sometimes also you need to this is a typical circuit where you use this energy which is collected, you can store by using thermal energy storage system, which is known as TES. And this thermal energy storage can be a latent heat storage, or it can be a sensible heat storage. So we need to do an effectivity analysis, cost to economic ratio analysis, or the performance analysis on how to optimize all this. How to optimize what is my area of my flat plate collector, how much is the temperature which is coming out, temperature out of this flat plate collector, and what is my requirement. So depending on the requirement, I can design my energy storage, and then that energy storage I can have a choice of latent heat or a choice of sensible heat. So this will, because why we require storage is because then you know that solar energy is not constant. It is very intermittent, depending on the weather conditions. So you need some energy storage, and that's why this is just like a mechanical storage that people use for the thermal energy power plants, like say for example pump storage or flywheels. Similar to that, we have thermal energy storage for this. So you can use this heat for the process heating, or even to produce electricity, or say during whenever you have cloudy weather. So there are hybrid systems where you can, instead of energy storage, you can use some other source, for example natural gas, to supplement the energy where the sun during the periods of low solar radiation. So so as to have the continuous operations. So that was all about the flat plate collector. Briefly, we just touched upon. There is concentrating solar thermal power plants where the rise in temperature for the flat plate was around 100 degrees centigrade, but we require, for power plants, we require more than this. So that we know that in the Rankine cycle, the higher the temperature, more will be the efficiency. So for generating the power from solar thermal systems, concentrating type of collectors are used. Now, how do you concentrate? So you concentrate by using, our objective is to have high temperature. That is the first objective, is to obtain high temperature. And you can obtain high temperature by using, linearization, basically. So you get concentrating linear systems, linear concentrating systems. For example, parabolic trough or linear piston reflectors. So that means it has a large number of collectors in a parallel row, and typically aligned, say north-south orientation. It is not east-west orientation; it is north-south orientation, so that surface can see, or the concentration surface, a parabola, can see the sun from various angles. So this is only one axis basically tracking. So typically aligned in north-south orientation. and enables the mirrors to track the sun from east to west during the day and concentrate the sunlight towards onto the receiver tubes. So there are these linear concentrating systems, and solar power towers is another design. So and then the third one is solar dish or energy system. So this is a typical presentation where you have the array of so parabolic trough collectors. So this is a parabola. You know that parabola has a focal length where you are going to on this focal length. You are going to have an absorber tube, and because the reflection area is more than the absorber area, so absorber area, so reflection area divided by the absorber area minus, basically you are going to minus this shadow that you have for the absorber tube, it will give you the concentration ratio. So for these kind of parabolic trough collectors where the focus of this parabola where you are located the pipe, the concentration ratio would vary from 30 to 100 times. So the concentration ratio which is CR is 30 to 100. So this will achieve the high temperatures as high as 400 degrees centigrade, and the world's largest or longest, you can say, operating solar thermal power facility, which is based on PTC, parabolic trough collectors, is in USA, which is a solar energy generating system in the deserts of California. So you can search about the operations of this. So basically, you have to have the working fluid. That could be water. Nowadays, there's a lot of research happened about what is the working fluid that we should use. Should we use nano fluids for the absorption? And then it is because you need to have a large thermal conductivity for this. So to improve the thermal conductivity, people use nanoparticles, say carbon or aluminum Al2O3 nanoparticles. Al2O3 nanoparticles are commonly used, and then you can extract this energy from the concentrator. So India's first solar thermal parabolic trough collector, so solar thermal PTC power plant, parabolic trough power plant is near Gurgaon, and it was with respect to, I think, IIT Bombay was overseeing that project, and there is a publication also out of this, the learnings that you have from this, and this is very recent. They're very recently established. India's first solar thermal PTC power plant. Similar to the PTC, we have this linear Fresnel reflectors where basically you reflect, and then there is another reflector here which will reflect on the absorber tube. So you have two reflectors basically, where first these are the reflectors, and then this is a linear Fresnel reflector which will reflect on the absorber tube. So again, this is used where array of reflectors are being used. The most commonly nowadays is heliostats that you see here. There is a central tower. You could see this is a central tower, and this central tower is heated to very, very high temperature. So concentration ratio would go up to thousands, and where all these mirrors, basically these are all mirrors, and these mirrors will concentrate solar radiation onto the respective tower. And in the tower, you have primary circuit. Basically, it could be a molten salt, or molten nitrate salt, or it could be a water. It depends on the temperature and the area of this collection. So if you are planning for a particular, and then how do you do sizing? You do the sizing based upon the output. So first you define your output that I want to build, say 20 megawatts or 22 or 10 megawatts of capacity. So if I have, that is the output of 10 megawatt at the shaft power, say after the generator, then you start calculating, and then you find out what is the steam required, what is the capacity required, what is the turbine size, and what is the pressure, and all. You put your cycle on the Rankine plot, have realization, basically real cycles, and then you can back calculate how much energy you need how much solar energy you need to concentrate to produce that much of steam. So depending on the optimization of the flow rate of your water, you can then that is directly dictated by your flow rate required for the steam flow rate or mass flow rate for the steam to compute that power, and then you can compute the area required for this kind of reflectors, say solar power towers. Okay, and then you can design. Similar to that, there is what is known as solar dish engines. So basically, it is a dish paraboloid shape. So where you get these mirrors, and these mirrors basically reflect it here. And this mirror dish is really composed of many smaller flat mirrors formed into dish shape. And this dish-shaped surface directs and concentrates sunlight onto the thermal receiver here, which is going to absorb and uh, collect the heat and transfer it to the engine generator. So there could be a Stirling cycle. So most common type of engine used in this kind of system, I think the text is not visible, is basically a Stirling engine. Stirling engine is based on the air as a working medium. So again, at the focus of this paraboloid basically dish, you are having this absorption, and again the concentration ratio is very high. Concentration ratio is very high. So that is summarizes basically what we looked at is various solar thermal energy systems, and why do you require these solar energy thermal systems. So I not touched the design of these and then what are the analysis, but one thing is sure, because you know that the solar energy is getting reflected or incident basically on these reflectors, or say on a glass cover for a flat plate. We know that the material on which the solar radiation will reach, it material, is going to absorb some of the radiation. So we have to talk about its stability. We have to talk about the temperature rise of the material itself. So if it is a glass mirror, then this glass mirror should be having large say reflectivity or large transmittivity, and then less absorptivity, so that the temperature of this glass itself is maintained to a low, and then there is no absorption of solar radiation here. Okay, so and then we should have these kind of films. So most of the material research also nowadays into manufacturing of these films, coatings, for example, and then these coatings are important, so that then it gives high reflectivity for the material. So high reflective coatings are really preferred for these kind of applications. So if you talk about the roles of mechanical engineers, before going to the civil engineers, we will talk about roles of mechanical engineers here. So we know that most of the solar thermal energy systems where you need to absorb the radiation, solar radiation. So you need to understand the fluid mechanics, to understand the heat transfer, you need to understand the heat losses from the system. So this is all thermodynamics of the system. So these are all what we call core subjects of thermal energy or thermal engineering. Apart from that, you need to also understand the structural designs, which will overlap with civil engineers also. But the say design of uh, the beams and design and the support beams and the forces acting. And when you talk about the moving of these solar reflectors with respect to the sun location, we are talking about the control aspect. So how do you control the temperature? How do you control the orientation? How do you control the flow of the fluid? How do you control the temperature of the working fluid? So there is a controls engineering, there is a design engineering, structural designing, and there is a mechanical, the thermal engineering, we call it thermal engineering, involved into this. So the roles of civil engineers for say CSPs, you know that you need to understand the site location, you need to understand the radiation that is measured, available site preparation. So mechanical and civil engineers can work together, and find out how do you prepare the site. So site, say, survey, labeling, foundation. Once you prepare the site for the particular project, you need to construct. So that construction is not that tricky as you would find it in, say, hydropower stations. Hydropower stations, you require civil engineers to play a major role, where you need to have a fail-safe design. Also, in case of nuclear engineering or nuclear reactors, you need to have a fail-safe design. But in the case of solar, we are not talking about not much of criticality here, but again, if it is a concentrating type of solar power, you require the construction to be foolproof, and this is where the civil engineers will play a role. Now, there is also stability of these structures. So if it is say solar thermal power station, by using parabolic plus array of parabolic trough connectors, or by using, say, central tower, they will be always subjected to wind and wind forces. So what is the stability of the structure for the wind? Again, with respect to solar photovoltaic also, you require this stability. And then you have roles for electronics and data science. We have seen that there is a lot of data that nowadays are getting generated. So we can put a lot of electronics also on the board. Say, for example, you can put a lot of IoT devices, and each section of energy nowadays, you can find out in each section of the energy supply chain, that is from generation to up to the energy grid, there are IoT devices. That means how you can understand the usage pattern. For example, how, say, particular locality, say in Karnataka. So what is the usage pattern of energy? Say people use energy probably in the households in particular way, and then you can then optimize your supply, and utilize other high grade energies basically for the industrial purposes and more in that. So that's how we can find out from the data, collection of data, and that collection of data requires a lot of IoT devices to be installed, and data acquisition system. So that's why data science engineers are also nowadays are required, so that they can create these dashboards, for example. So I can create a dashboard of say Karnataka, where I would say that, okay, this is what I have. Nowadays we don't have blackouts. Earlier we used to have blackouts, but nowadays less blackouts. But still, you can optimize your supply and demand for energy, so that you get energy efficiency, and you can integrate these renewable energy sources very efficiently. So to the grid, supplying it to the actual grid is a challenging task. So that's why people go for what is known as microgrids. So where you have not the central grid, like we know that India is divided into 4 to 6 grids. Okay, central grid and then southern, like that. But you can have a microgrid particular for particular region, and you can start using the renewable energy. So we have to increase this. So energy usage. So data collection and analysis of energy generation, usage, pattern recognition, machine learning are emerging trends, emerging what you call subjects in the energy sector. So these are the references that I have taken. I have taken from web sources, few figures from some book. There are this IoT and energy in the energy sector. This 2020, there is this review, and this India's first solar thermal parabolic trough power plants in 2014 it was with IIT Bombay. You can see that. So I hope that India builds many thermal energy based power stations. If not, we can have small stations or small power plants where it is for a particular village. We can have, say, for example, if it is agriculture based, we can start thinking about solar thermal storage, solar thermal the dryers for the food preservation. And if it is, say, the city region, if you want to do say baking, so then solar ovens, solar cooking. So then solar heating, you know that most of the now households in at least in the southern part we have solar heating, and many households are now coming up with solar photovoltaic for solar power generation. And that is a good thing that we should move to this renewable energy source. Very low, less percentage of energy source is basically from the from the renewable energy sources, and the contribution of solar energy is very less. The Duffy Beckman book is, I felt it's very nicely written. But if you look at Sukhatme and Nayak from IIT Bombay, these professors, they have this solar energy principles of thermal collection and storage. This book is specifically for thermal collection, and this you can refer. All the data that you have for this is Indian data. All the data that they have given in these books are US data. So this book can be taken as a reference. So thank you, and I will take some questions.
Hello, sir. This is Dr. Vignesh Kulwal. I'll be reading out the questions. Yes, sir. I'll be reading out the questions. So the first question is from Mr. Sorup, who asks how to measure efficiency of solar photovoltaic cells.
Okay, so solar photovoltaic I am not covered. See, solar photovoltaic cells. Hello.
Yes, sir.
Yeah.
Please go on.
Yeah, you can mute. Yeah. So solar photovoltaic collectors. Solar photovoltaic is basically you can test when you do a particular material, basically a semiconducting material, and you prepared a panel, solar panel. Then what you need to do is understand the IV characteristics, that is current voltage characteristics, and short circuit current and short circuit voltage. So if you can establish that IV characteristics for solar photovoltaic, then you can say that this is a material that you have developed and this is the IV characteristic. Now the efficiency of this solar photovoltaic depends on the stability of the material. Okay, so the efficiency depends on the stability of the material. Yeah. Nature. I think somebody nature first.
Yes,
yeah,
sir.
go ahead.
Sorry.
Hello.
Yes, sir. You have a question, Mr. Nature first. Okay, sir. I think he has muted himself.
Yeah.
Please continue.
So what I was saying is that this efficiency of the solar photovoltaic material actually varies with the usage, because the material itself degrades. Nowadays, the material degradation has reduced. They are very much stable. The material that is being developed, so it can be useful for years together. But the thermal characteristics, what happens to this material when you are at high temperature. So that's why solar photovoltaics are also coming up with what is known as solar PV thermal. So where you pass the water underneath the solar panels, so that the solar panel temperature itself will be reduced. Because we know that whenever solar panels will have one glass cover, say 2 millimeter thickness, and this through this glass cover, the sun radiation is radiating on these solar panels, solar photovoltaic material, and this material is unstable at higher temperatures. So you need to control the temperature. If you control the temperature, you can optimize the efficiency of the solar panels.
Yes, sir. Thank you.
Yeah.
The second question comes from the same person, Mr. Swarup. He asks, can we increase efficiency of solar photovoltaic cells by providing exterior cooling? I think you already answered this.
Yes. Efficiency certainly you can increase. Nowadays there are what is known as floating solar PVs. Although I have not covered that's why I didn't putting PV or PVT here in the talk. So for those photovoltaic systems where it is kept not on the ground but on the water body, which has a lot of advantages. Like for example, you will reduce the evaporation of the say water. So there are you might have seen in the Gujarat and all, you have projects where they have kept the solar photovoltaic panels on the canals. So the objective is that canals underneath will cool the solar photovoltaics panels. So these PV panels are certainly kept on the water body, say floating PVs, they will be efficient.
The next question is from Mr. Natrajan B. The question is, the cheap and best fluids having greater thermal conductivity property, lesser corrosive property other than water is used for commercial plants. So he asks, what is that fluid other than water which has greater thermal conductivity and has lesser corrosive property and which can be commercially or which is commercially used?
I don't know the actual commercial grading or something like that, but there are what is known as hot oils. So you can search hot oils for thermal systems where they have been used for purposes over the years. But nowadays, if you look at, there is a lot of research has happened to use nanofluids. So nanofluids with Al2O3 nanoparticles, Al2O3 nanoparticles embedded in a fluid, which could be used in a primary circuit. Again, we are talking about a primary circuit where you will extract a lot of energy through the collector system, and then in the secondary circuit you will heat exchange that by using heat exchanger and use for some particular use. So hot oils and nanofluids are used as alternatives for water.
Okay, sir. So the same person asks, shall we use Fresnel biprism other than glass windows to enhance the efficiency?
Sorry, can you please repeat again?
Shall we use Fresnel biprism other than glass windows to enhance the efficiency?
Yes, it depends upon the the collector system that you are looking at. So there are compound parabolic collectors, these Fresnel reflectors. So it depends on the design of your system. So there are various patents now coming up with new designs. See, earlier we okay, this is the particular parabolic trough collector and this is how we should. But I haven't seen so far where you have combination of many and how do you localize it. There are what is known as covered for parabolic trough collectors. Covered means it is like a transparent glass cover, okay, where it is like you have that green agriculture, where you house the plants in a particular greenhouse, and then you plant that. So just similar to that, you have covered parabolic trough collectors. Covered parabolic trough collectors will reduce the convective losses. In order to arrest the convective losses, they have this. So similarly, you can have various designs where you can look at the concentration of solar radiation and the energy in a particular environment. Now the heat is maintained and the losses are minimized.
Okay, sir. The next question is from Mandar Sumant. Where we can use the parabolic trough collector and what will be better, flat or parabolic collector? There are two parts, sir.
Yeah. So again, it depends upon the end use and the rate at which you require the energy. Are you going to store the energy, the heat energy that you have? So the flat plate collectors are generally used at low temperature applications, and the parabolic trough collectors are used because it's of concentrating type, is used for high temperature applications, high temperature process heating, for example, and then it also depends upon the cost, the economics of the plants. So we have to do a proper selection once we come to the requirement. So it could be either flat plate, or it could be array of flat plates, or it could be array of parabolic trough collectors.
Thank you, sir. I have a question for you, sir.
Yes.
What are the characteristics of molten nitrate salt that make it suitable as a heat transfer medium in the case of solar energy?
Yeah.
Any thoughts, sir?
Uh, Characteristics of nitrate. So no, I don't have exact answer for that.
Okay, sir. Fine.
Yeah.
Uh,
Yeah. What I understand is this
behalf,
conductivity and
sir?
then the stability. The stability. That means what I understand is this fluid that you have in the primary circuit, it will be stable at higher temperatures. It will not. It will not evaporate. It will not change its phase. Okay. So there is no phase change. So we have to, because it's, see, if I use water in a concentrating tower, and then what will happen is, because the temperature itself is around 500, 600 degrees centigrade, okay, in the concentrating, if I use water in the primary circuit, then what happens, I will get generation of steam, and it will not be a continuous flow. Okay? So that's the reason people use, in the primary circuit, a stable fluid which will not change its phase.
Okay, sir. I think there are no further questions from the audience. With that, we will come to an end of the Q&A session. On behalf of the Mechanical Engineering Department at Mangalore Institute of Technology and Engineering, I, Dr. Vignesh Nayak Ullal, would like to thank our speaker, Professor Dhiraj Patil, for providing us elaborate information regarding the systems that are used for solar thermal energy production. Thank you very much, sir.
Thank you for this opportunity, and I hope I have answered the questions. I have shared the slides again in order to put some perspective. I have didn't go in depth, for the thermal analysis, or so that, because I was told that there is a mix of faculty members for this FDP. So I hope I would interact with you all in near future.
Sure, sir.
Yeah, so you can write to me if you have any further questions.
Yes, sir. So we come to an end of session 1, which involved which involves solar thermal energy systems.
Shall I stop presenting now?
Yes, sir. Please.
Thank you. Yes.
So the next session will begin at 11:15. Our next speaker would be Professor Arunachal U. Chandawar, and the topic would be thermal management of photovoltaic modules, recent advances in parabolic trough collector.
Okay, thank you. Thank you, everyone.
Thank you, Professor.